There we are. Today is lecture 7, and it's going to be the first of what I think is going to be a two-part series. You'll notice we've had a lot of those two-part series already. I'm often ambitious about how much we can cover in one lecture, and so things are starting to stretch out a little bit. We could, in theory, do all of initial orbit determination in one lecture if we were comfortable sitting down for 2 hours to do it. But A, I don't want to make you do that. I know you have other things to do. And B, I recognize that there's a homework due tomorrow, and we might want to stop and talk about that for a little bit. So there's 3 methods of orbit determination that I want to go over, and we're going to talk about the first 2 today, and then we're either going to start the third or we'll kind of call it and stop and move on. And so we'll just see how far we can get with the time that we have. And then we'll finish up orbit determination next class, and then also talk about matrix vector calculus. So let me share my screen for a second here. There we go. And so I like to kind of come back to the course map from time to time. So hopefully everybody can see this here. So this was the map that I showed on the first lecture of everything that we're going to cover in this class. And we are still living in orbital mechanics land, so understanding the way that things propagate. Although I would argue that today's lecture is orbital mechanics verging on navigation, and you'll see why in a bit. What we're about to move into is this area down here with the abacus underneath the turtles, which is labeled estimation theory. So for reference, everybody knows the Earth is sitting on the back of a giant turtle, and that underneath that turtle is another turtle, and that it's turtles all the way down. And at the base of that is mathematics. That's why I kind of have this over here, because math is the basis of everything. We're going to get into some mathematical tools that we can use to describe variables that have uncertainty in them, which is how we're going to model our state, and then how we treat that uncertainty, how we measure it, how we quantify it, and then how we can perform operations to estimate uncertain variables given measurements. And so all of that falls under the branch of what's called estimation theory. So we're going to be getting into that unit in a little bit, and that is the backbone of everything else that we do. But even more fundamental is orbital mechanics, kind of the physics that's underlying everything else. So we're still kind of smack dab in the middle of orbital mechanics. We'll be done in actually I think next lecture might be kind of getting into the end of that, getting into the math, and then we'll be spending some time on estimation theory. Then we'll talk about navigating using measurements from the Earth of a spacecraft, or navigating on the Earth using measurements of a spacecraft, i.e. like GPS or global navigation satellite system. And then we'll move on to what the spacecraft can do more or less on its own, and that will be the later parts of this course. So it's good to come back to the course map just to talk about this so that we know where we are, because I know it's really easy to get lost in like, okay, what are we on now? So today is orbit determination. And so let me pop over to, there we are, initial orbit determination. So I'm going to start by drawing a picture, and then I will ask somebody, whoever's feeling brave, to pipe up and answer a question. So I'll take a volunteer while I try haphazardly to sketch something here.
I can volunteer, Paul.
All right, appreciate you, Kevin. So let's say that you've got 2 stargazers, which are not to scale. There we go. And they're looking up at the night sky. So let's put some stars up there. Maybe there's a star here. Yep. I think 7 is a good number of stars. And let's say that at some time they can see a spacecraft. And then at some later time, spacecraft is here. And then at some still later time, the spacecraft is here. So they're watching a spacecraft streak across the night sky like a shooting star. And so my question for you is, I guess 2-part question. Is it possible to find the orbit of the spacecraft from these measurements? And if so, how many would you need?
Yes. I'm sure you can figure it out.
Nice.
I think you
Want
would
to hazard a
need
guess of how many?
3.
It is 3. Very good. Excellent. And we're going to talk about why it's 3 in a little bit. And so the other thing that we're going to talk about is if we Well, let's just get into it. I think that's a good enough primer. So that's what we're going to be going after is you've got this ability to observe something from the Earth, you watch it track across the sky. Can we use that information to determine the orbit of the spacecraft? And so part of this is going to be orbital mechanics because we're going to be talking about the motion of bodies in space, but it is also navigation because we're trying to determine the state of something. And remember, that's what we're after, right? Navigation is determining the state, position, velocity, acceleration of some object in space. So thank you very much, Kevin. You are off the hook and we are off to the races. So initial orbit determination is, so IOD, initial orbit determination, which we are going to abbreviate as IOD, uses, or I guess to say, let's treat it this way. Sorry, not uses. Is the use of measurements of an orbiting body to estimate its state. Typically, under the assumption of two-body motion. So we're going to leverage the physics that underlie two-body motion to solve a lot of our math problems here. So we'll start down here. By contrast, determining the path a body will follow with a high degree of accuracy and this is, for example, accounting for perturbations, etc., is precise orbit determination, or POD. And we will not be discussing that in the class. So we're starting with the initial orbit determination. Cleaning that up for a better estimate of how something behaves is precise orbit determination, which is outside the scope of this class. So we're happy once we found the position and the velocity of an orbiting body under the assumption of two-body motion. Precise orbit determination involves answering a few other questions, determining a few other variables, taking into account perturbing effects and body motion, so on and so forth. We're going to leave that for another day. So when performing IOD, I'm going to take another brave volunteer to answer a question. When performing IOD.
I'll go.
All right, excellent. The objective, hang on one second, is to find what? So let me ask you this question. When we're performing initial orbit determination, are we done once we've found the position and the velocity of the orbiting body, or are we done once we've found the classical orbit elements that go along with that orbiting body? When are we done?
So don't you have to like get the position and velocity and then use that new position and velocity to find the orbit elements at that like position?
Okay. So I think we're saying the same thing. So let me clarify that a little bit. So if I have R and V at some time, am I done? Is that when we declare victory? Or when we have the orbit elements, are we
The
done?
orbit elements.
Orbit elements. Actually, I hit you with a trick question. I'm sorry to tell you.
Oh.
Either one is the thing, right? Because if we know position and velocity, don't we also know the orbit elements?
Oh, yeah.
We can find those. And if we know the orbit elements, we can find position and velocity. So even though there's a lot of math going back and forth between those, by the end of homework 1, it should be, you should be roughly to the point where if you know R and V, I'm just one MATLAB function away from knowing theta, omega, EA, all the other usual suspects, and then vice versa. So sorry, I'm sorry to hit you with a trick question, but I think you're thinking along the right lines though. So I like to see that.
Yeah, that's kind of what I said at first, but then I got confused because I thought it was a trick.
Was it you were too smart? It was a trick, and then we got all screwed up. That's fine. But I think the main point is that everybody understands. The objective is to find either all 6 orbit elements or more commonly position and velocity at the same time. If you know the position at some time and the velocity at some other time, that's no good. You need the full state, the full translational state at the same time. And remember that we know that these are equivalent pieces of information. That's what I was getting at before. Equivalent pieces of information. There we go. So we will discuss 3 classical IOD approaches and 1 modern one. So one case is if you know 3 positions. So you know the position of a spacecraft at some time, and then you know the position of the spacecraft at some other time, and then you know it at some third time. There's a fellow named Gibbs who can help us. If you have 2 positions and you have delta t, the time between them, then that is what's referred to as Lambert's problem. Well, I'm just going to say Lambert for now. Good enough. And then finally, we'll scroll down a little bit here. If you know 3, what's called line of sight measurements, which is kind of what we were discussing at the beginning, right? You've got some observer on the Earth just looking up at the sky. The classical solution from the early 1800s is called Gauss's method, but there's also a method from the 1990s called Gooding's method that we'll be talking about. So very good. And so that's what we're going to be discussing today. I think we're only going to have time for Gibbs and Lambert, and we're going to leave Gauss and Gooding to next class. Gooding is just, we're going to have a cursory, very high level discussion of it. Whereas Gibbs, Gauss, and Lambert, like by the end of what we're talking about, you will be able to code up your own Gibbs, Lambert, and Gauss. And part of the reason that we're doing this now, I mean, this is the natural progression of lecture, but also your homework 1 extra credit asks you, if you're interested, in going through and performing orbit determination using 1 or more, perhaps even all of these methods, just to verify to yourself that they work. I would highly recommend looking at least at Gibbs method, partially because Gibbs method, having that working is going to be required in homework 3, I think. So you might as well put in the time to do it now. I recognize that there's a finite horizon between now and when the homework is due. We got about 24 hours. I think from what it sounded like in office hours, most of y'all are almost done or completely done, which is good. If I were in your shoes, I would spend 1 hour on Gibbs method. And if it comes together and you have the code working, great. And if you don't, I would just eject and go do something else. That's my advice, but I recognize y'all are juggling different things than I am. So we're going to start with Gibbs method, but before we move on, any questions up to this point? So far, so good. All right, let's get to it.
I have a quick question. What does the more modern method use?
The more modern method is Gooding, which is also 3 line of sight measurements.
Ah, I
So
see.
the observables, yeah, it's not so much that we're using different observables, although there are even more modern methods from the 2010s that use different observables besides position, line of sight, and time. There's one that's less than 3 years old that uses only heading measurements. We can talk about that too. So this is like still an active area of research, but the classical, like, people from the 17 and 1800s, the main solutions that you'll learn about. So especially if y'all took orbital mechanics with Dr. Anderson, he would have at least nodded to these three methods, and they're in your textbook, your Howard Curtis undergraduate textbook. Um, I'm not sure what Dr. Singh covered, if it was these or if he didn't talk about them. But these are kind of the, you know, introduction to IOD, kind of the three main methods that people learned. So Gibbs method was invented by Josiah Willard Gibbs, who lived from 1839 to 1903, who studied at Yale his entire career as a student and then as faculty. So he was, among other things, the first ever doctorate in engineering in the US. So this long line of people getting PhDs or Doctor of Engineering or whatever it is, he was the first who would to get a doctorate in engineering. He was also, among other things, the father of modern vector notation. So when we store vectors like this, and we store matrices like this, and then we go, okay, it's the first row of the top times the second row of this is equal to the first element here, and then the second row of this times this is equal to this. All that was Gibbs. Right, so he invented that. And so naturally it would follow that the Gibbs method of orbit determination is very heavy with vector math. There's going to be a lot of fun vector math coming up. So let's get a nice little picture going here. Why don't we change colors and we'll make this the Earth. Nice little sky blue going. So let's say this is the Earth. And let's say that you've got some reference frame, because we love those. Not exactly worried about which reference frame it is at the moment. And let's say that you've got some unknown orbit, which I'm going to draw as a dotted line here. And you've got some position vector here, which we're going to call R1, some position vector here, which I'm going to call R2, and some position vector here, which I'm going to call R3. Right? You've got three positions. So Gibbs method of IOD finds a conic section, and we're going to focus on closed conic sections, i.e. ellipses, that connects three position vectors. And so the problem looks like this. Given R1, R2, and R3, find VI, where I is any of those. Could be V1, V2, V3. Because if you know V1, R1, V1, that's your full state. You've solved the problem. If you know R2, V2, if you know R3, V3, knowing any of those, you're done. You can declare victory, right? So that's what we're going to be trying to accomplish here. So let me start with a question here. The question. Why is three position vectors enough? right? How much information do we have in three position vectors? Or you could think of it this way, right? In general, if you're trying to solve a problem of fitting an ellipse to points, because that's basically what we have, right? You've got some point here, some point here, some point here. You could fit a circle to 3 points. How many points do you need to find an ellipse? Does anybody know that?
I think you need 4, and you've kind of got a sneaky hidden fourth point at the center of the Earth.
Ah, that's almost exactly correct. So you would in general need 5. You need 5 to find it. But you're absolutely right. The fact that we know that we're orbiting the center of the Earth actually gives us, you could think of it as giving you 2 other points because you get your focus and you get your other focus, right? So given that we know this is an orbit, we now know, and we also know that these points are going to be coplanar, we can essentially say, okay, um, in general, we would need 5 points on the edge of an ellipse to declare victory. But because it is a 2-body orbit that is orbiting about the center of the Earth, we would only need 3. And so you can think of it in terms of the degrees of freedom, right? And how much information you have in each of those. So very good. Appreciate it. That was basically exactly what I was looking for. So, okay, we will begin again with the equation for eccentricity. Okay. So E is equal to velocity crossed with h over mu minus r over r. So this is not news, right? We've talked about this before. And I'm looking at my next page of notes, and we are about to embark on a mathematical adventure, the likes of which you've never seen. So if I start to go too fast, or if I'm scrolling too fast, just let me know, and we can go back up. Yep. So we're gonna now move some things around. Hopefully, it's clear that we could solve this for v cross h is equal to mu r over r plus e. Hopefully that's straightforward. All we did, multiply both sides by mu, add r over r. Okay, so far so good. So this is where I hate it when professors say, and then we skip a few steps. However, if we don't skip a few steps, it will take more than one lecture to do Gibbs method, let alone all the other methods. So after some manipulation, and I'll leave this as an exercise to the reader, this becomes that your velocity is mu over h squared, and that's h the scalar, times h crossed r over r plus h crossed with e. And so this is going to take a lot of fun vector manipulation. Remember, Gibbs is the father of vectors, essentially. Now we can actually take some shortcuts here. Recall that by definition, your E vector is really your E scalar in the P hat direction. Remember the parafocal direction? And that's kind of just because we defined P as pointing in the direction of the E vector. And similarly, your H vector is really your H scalar in the W hat direction, because W is the direction that points in the direction of H. And so we can kind of work with this a little bit more, and this becomes that your velocity is mu over single h w hat crossed with r over r plus e in the q hat direction. All right, so all we did was make these substitutions and then work some things around. So what this means is, because remember, we're ultimately after velocity, right? We're ultimately, if we know v at some r, we're happy, but we don't have all the information just yet. This means that if we know h the scalar, w the direction, and e times q together, we can find V as a function of R. So we need some analytical expressions for H, W hat, and E times Q hat as functions of the three position vectors. And if we have that, we're basically good to go, right? And so join me, why don't you, as we start down that path. So there is another critical observation. And that is, and this might be obvious, that all position vectors on an ellipse, or a hyperbola for that matter, must be coplanar. Therefore, that's what the three dots means. One is a linear combination of the other two. So I'm going to give you a second to catch up on that. But what I'm saying is, if we know that there are three position vectors and they all are in a flat plane, that means that some combination of R1 and R2 must give you R3, or some combination of R1 and R3 must give you R2. And so that's what we're going to say. We're going to say that R2 is some coefficient times R1 plus some coefficient times R3, where C1 and C3 are unknown, and we are going to find those later. And these are what's sometimes called the Gibbs coefficients. Okay. What that also means is if we say R2 projected onto E is equal to C1 R1 transpose E plus C3 R3 transpose E. Okay. Why do we care about that? Well, you might recall that R transpose E is H squared over mu minus R. And this might be a recall situation. This might be this is the first time I've seen this equation situation. That's fine. We're going to combine this equation and this equation to say, okay, H squared over mu minus R1 is equal to C1 H squared over mu minus R2 plus C3 H squared over mu minus R3. Hopefully that makes sense. And then this is where I have to pull another one of those sleight of hands and say, after quite a bit of manipulation, this becomes, and this is where Gibbs landed on a really beautiful set of equations. Like I'm amazed that it works out this way. It's so nice. We're going to define some new thing called n. It's equal to h squared over mu times d, where n is R1, apologies, R1 the scalar, times R2 crossed with R3, plus R2, R3 crossed with R1, plus R3, R1 crossed with R2. And D is equal to R1 crossed with R2 plus R2 crossed with R3 plus R3 crossed with R1. And so what this means is you can compute N and D from the stuff that we started with. They are this really interesting symmetric kind of combination with cross products and dot products of the original three vectors that we started with. That will allow you to find N and D, which are both vectors. That's why they have a little hat. And then that would mean that we could also find H. Sorry, did I hear, I thought I heard a question, but I could have just had a hiccup on my computer. Good, okay. So let's just formalize that for a second. There we go. One can compute N and D from R1, R2, and R3 to find H. So we could say H is equal to square root of mu N over D, where it might be clear from notation that N is just the norm of N like this, and D is just the norm of D like this. Okay, so checkpoint. We found H. I'm going to scroll up. Don't worry, I'm coming back. We've established if we know H and we know W and we know EQ, we can find V as functions of R. So next we need to go find W as functions of R. Okay, now bear with me for a moment. If we looking more closely at D, it must lie along which direction? So I'm going to open this up to the class. If you look at the D vector, which way is that pointing? It's R1 crossed with R2 plus R2 crossed with R3 plus R3 crossed with R1. So I'm not asking for a magnitude, I'm asking for a direction. So get your right hand rule out. What direction is D pointing in? Any takers? And I'll scroll up to the little diagram up here. R1 crossed with R2.
It's just out of the plane, perpendicular to the plane of the orbit.
Ah, very good. Excellent, Renee. It must lie along the W direction, which is the perpendicular plane to the orbit. So let me put that in parentheses. Perpendicular to orbit plane. So get your that was easy button out, because W is just the D vector divided by its own magnitude. Wow, okay, nice. So let's scroll back up. If we know H and we know W and we know EQ, we are happy. Next is EQ. So finally, we need eccentricity as a scalar times the Q direction, which is really three numbers if you think about it, right? The Q direction scaled by E is three numbers. So we're after three numbers. So recall that the Q direction is just what happens when you take the W direction crossed with the P direction, right? Okay. So therefore, Q is W crossed with, remember, P is the direction that we get from the eccentricity vector. So P is really eccentricity divided by its own magnitude. Okay. Now, we just said W is D vector divided by D magnitude. So D vector divided by D magnitude crossed with E vector divided by E magnitude. All that is Q. So EQ is the same as D vector crossed with E vector divided by D magnitude. Okay. So far, so good. So if we know D, we just need the E vector and we've saved the day. Okay. Well, we don't even necessarily need the E vector. We just need D crossed E. And this is another one of those very unsatisfying using some additional manipulation. And if this were an IOD class, I would be in big trouble for skipping this many steps. But this is an introductory course. I just want you to know that this technique exists. Using some additional vector manipulation, one can show that there is something which we will call S, which is equal to D crossed with E, and that's equal to R2 minus R3 R1 plus R3 minus R1 R2 plus R1 minus R2 R3. Therefore, we can say that EQ is really S divided by D. Okay, so we're going to scroll back down in a second, so don't worry if you're not quite caught up to where we are. But I would argue that we are now ready to declare victory because we have H, we have W, we have EQ. All of those are wildly, well, maybe not wildly complicated, but reasonably complicated functions, but ultimately just dot product and cross product combinations of our three position vectors, which is really cool the way that works out. So our original equation for velocity from up top becomes, we're gonna have a couple steps here. V is equal to mu over H, D crossed with R over dr plus S over D. Or we could do some factoring. That's mu over H capital D, D crossed with R over R plus S. But still not quite there. This mu over HD, I'm not quite sure I love that. So remember that H, if we scroll up here, H is square root of mu n over D. So if we do a little bit of substitution, I'm just doing this to clean up our equation here. Mu over HD, which is kind of this part here, is really mu over D times the square root of D over mu n, which is the same thing as mu over square root mu times square root D over D times 1 over square root n. And this becomes the square root of mu over nd. I just find that a little bit more fun to look at rather than mu over hd. It's kind of your choice. But I don't like that h is something else that we need to compute. I like it to be nice and clean. So our final equation is going to look like this. Velocity is equal to square root of mu over n d, d crossed r over r plus s. And this gets a nice red box to go along with it. And you might be thinking, okay, why are we declaring victory? Well, let's review, right? D, S, N, those are all things that are combinations of the three position vectors, and we can compute those. And I guess what we should really say is VI is some function of RI, right? Because it's for a specific position, you can find the corresponding velocity, which is very cool. So to recap then, the Gibbs procedure is, the Gibbs method procedure is, maybe I won't do the underline. There we go, it's going to be confusing. Step 1, use position 1, position 2, position 3 to compute N, D, and S. Next, calculate VI corresponding to any RI of your choice. And then 3, if desired, your choice, you can say RI and VI can be used to compute theta I, E, A, omega I, and omega, right? You can find the orbit elements. That's if you want to. So on the homework, what this would look like is, if you wanted to code it up, you would need to write a function that takes in R1, R2, R3, and it computes N. So these are about to get some stars here. Computes N, computes D, and if we scroll down a bit, it computes S. And then it uses this equation to find V, and then it spits out R and V. And then you could use a different function, which I'm assuming you might have already written, to go from R and V to the orbit elements, or not. And you can compare, okay, if I cook up 3 positions at 3 different times in my orbit, and I run them through this equation, like you actually know because you have the SPICE data. Is that the right velocity? Let's see how close I got, that sort of thing. So that's what I would challenge you to attempt on homework 1. This is going to be very useful. Knowing that once we have 3 positions, the day is basically already saved is definitely useful. And this is, congratulations, our first navigation problem in this class because we are estimating R and V given a set of measurements, right? So we're kind of well on our way to being navigators. All right. So that's a natural pausing point. I'm going to stop there before we discuss the next orbit determination method. So if anybody has any questions, now is a great time. Otherwise, we're going to take a break. And I'm going to say back at 7:01.
I have a question.
Yeah, absolutely. What can I do for you, Talia?
Is RI calculated from VI or do we already have RI?
So we're assuming that we start with 3 position vectors. So you've got R1, R2, and R3 going in. And then you pick, you can compute V1, V2, or V3, or all 3 of them if you want to, right? But it's kind of redundant. Let's say you did R1, V1, then we're happy, right? There's your orbit determination right there. But yeah, you're trying to find V from R.
Oh, okay. So we just put an I there because it could be 1, 2, or 3?
Yep, I just leave it open to whatever your favorite is.
Oh,
You might decide that you want your position at the time that you started taking measurements. You might decide you want the position at the most recent time. You might want the middle one. It's kind of dealer's choice.
okay. Thank
Yep.
you.
Absolutely. All right, I think we'll get back to it here. All right, so people are hopefully pleased with Gibbs' method. There were a few maybe not super satisfying, kind of skip a few steps in the derivation, but hopefully you appreciate that that's necessary to keep this down to a reasonable amount of time. Lambert's problem is next, and it's also going to have some fun math and skip a few steps here. Really, each of these, deserves its entire own lecture, maybe multiple lectures to discuss each of these. We're trying to kind of go rapid fire here. So next is what's called Lambert's problem. All right. So Johann Heinrich Lambert, and I just realized I don't have the date that he was alive like I do for Josiah Willard Gibbs. So we're just going to keep moving. Johann Heinrich Lambert posed the problem, which is interesting to me that he posed the problem and then didn't solve it, and it's still named after him. Posed the problem of finding an orbit given not 3 position vectors, but 2 position vectors of an orbiting body and the time of flight between them. And so what that makes me think of is we've got some sort of delta t going on here. So whereas our first set of equations for Gibbs' method were heavily dependent on R1, R2, and R3, all of a sudden now we're going to have to start thinking about delta t, and things are going to be a lot less pretty. They're going to be a little bit more ugly for solving Lambert's problem than they were for solving for Gibbs' method. And so the problem was solved. I wish I had the date, but it was late 1700s, early 1800s. This problem was solved by Joseph Louis Lagrange. Yes, that Lagrange, using some coefficients that he calls the Lagrange coefficients. Joseph Louis Lagrange. And so our problem is going to look like this. Let's get another picture of the Earth going here. So we've got the Earth. And let's say we've got our, yes, thank you, that's plenty. Let's say we've got our reference frame here. And let's say we've got some orbit that we don't fully understand yet. And let's say we've got some position 1 and some position 2. And let's also say that we know delta t between them. So the problem looks like this. Given, oops, all right. OneNote is just starting to get a little bit feisty, start fighting me here. I hope I don't have to restart it. But the problem looks like, given R1, R2, and delta t, find V2. OneNote's actually being a little bit more stubborn than usual right now. Uh-oh. Whoa, all right. Am I back?
Yeah, but you're not showing your screen
Okay.
anymore.
Yeah, I turned off my screen. Sorry about that. Yeah, I had some huge connection hiccup on my end. Sorry about that. I'm hoping that's a one-off. Let's see. If that becomes the situation, I might need to check my router. Let's see. Are we still recording? Okay, good. All right. Apologies for the hiccup. Let's pick up where we left off here. So, given R1, R2, and delta t, and also we're going to need mu. We need to know the thing that we're orbiting. So that's kind of a given. Find, and what we're going to look for is V2 specifically. That's our problem. That's Lambert's problem. So we're going to begin. We will begin with Lagrange coefficients, which you might have seen in your beginner orbital mechanics course. R2 is some linear combination of R1 and V1, F R1 plus G V1, and V2 is some linear combination of R1 and R2, which we're going to call F dot R1 and G dot V1, where, let me just make a little space here, where F dot, G, and G dot are what's called Lagrange coefficients, which clearly have something to do with time, because they're allowing us to map from some position and velocity to some future position and velocity, right? So these might seem a little bit magical on the surface, but we're going to talk about where they come from, how to compute them. So we can actually rework things. We can say, okay, V1, velocity 1, is 1 over G, R2 minus F R1. And V2, which is kind of the one that we're after, is 1 over G, G dot R2 minus R1. Okay, but remember R2 is F R1 plus G V1, right? So we're going to use R1 and R2 to try to build V2. And it's okay, so we've got V1, all right, R2 goes there, sure, so far so good. The problem then is that we need the Lagrange coefficients. All right, so now things are going to take a bit of a left turn. we now introduce a kind of one-off character, something called universal anomaly, which we're going to give the letter chi. Looks like an X, which is valid because we don't necessarily know whether this is an ellipse or a parabola, right? So this is or ellipse or a hyperbola for closed and open orbits. There we go. And so if chi is 0 at some time t equals t naught, then chi as a function of t naught plus delta t is found by solving the universal Kepler's equation. We knew Kepler was going to play a role in this somewhere. As soon as we saw time, it's like, yep, okay, changing position as a function of time. So here's the universal Kepler's equation. It looks like this. Square root, as soon as I can write again here. Square root of mu delta t is equal to r naught v naught over square root mu I squared c of z plus 1 minus 1 over a r naught pi cubed s of z plus r naught. I'm going to restart OneNote in a second here because it's getting kind of squirrely. So this is where I don't necessarily love most derivations of the Lambert's problem involves kind of this sleight of hand, which feels a little bit cheaty to me, where it says, okay, by the way, didn't you know about universal anomaly and the universal Kepler's equation and some other things we're going to talk about? Like, I'm sure that when Lagrange was thinking this through, he spent a long time thinking about it and finding some great ways to solve it. However, I just feel like at a beginner orbital mechanics level, this feels a little bit like what's the word? Deus ex machina, right? Whenever somebody just gets saved by the bell in writing, feels a little bit cheaty. Let me go ahead and restart OneNote here because it seems to be acting up. No, thank you. So anyway, there it is. I'm not thrilled either because it just kind of gets thrown at you. And actually, there's even more to it. So bear with me for a little bit. For now, we're just going to say there exists this fun equation where z is equal to chi squared divided by a. A is in this case the semi-major axis. And c of z and s of z are what are called stump functions. In case you haven't seen those before, c of z is the sum k equals 0 to infinity, -1 to the k, z to the k over 2k plus 2 factorial. And s of z is k equals 0, -1 power k, z to the power k over 2k plus 3 factorial. So these are a class of functions called stump functions, named after first name Stumpf, which are useful here and here, right? So this is the part I don't love, is where this just gets dropped out of the sky. Fortunately, from this point forward, things actually become a little bit more clear, right? So this fun universal Kepler's equation drops out of the sky, along with these stump functions and along with the idea of universal anomaly. But things are going to start to come together. So after some manipulation, we can solve for the Lagrange coefficients. Remember, that's what we're after. So F, and remember, we actually only need F, G, and G dot. We don't necessarily need F dot. F is 1 minus chi squared over R1 C of Z. G is delta T minus 1 over square root mu chi cubed S of Z. And G dot is 1 minus chi squared over R2 as a scalar, C of Z. Okay, so we've got our 3 Lagrange coefficients. So what this means is, if we know chi, and if we know Z, then if you know Z, you can evaluate the stump functions. If you know chi and you know Z, we can solve for F, G, and G dot. Okay, so this is starting to come together, all right? So some further analysis. Will show that chi is itself the square root of some function y of z divided by our stump function c of z, where y of z is equal to r1 plus r2 plus some a, which we have not been introduced to yet, z s of z minus 1 over square root c of z. And a is equal to the sine of delta theta square root of r1, r2, 1 minus cosine of delta theta. Okay, great. So does this help us? We've had a bunch of equations just kind of thrown at us. All right, how is this exactly going to help us? So there's one last thing, and then we can pause to kind of catch our breath here. If we assume that we are on an elliptical prograde orbit, prograde meaning that if you take R1, cross it with R2, and you take the z component of that it's positive. Or another way of saying that the normal vector is more aligned with the global positive z direction than the negative positive z direction. So we're kind of in a counterclockwise orbit, right? That sort of thing. Then we can take a little bit of a shortcut and say, okay, delta theta, which we just discussed, is just the cosine inverse of R1 transpose R2 divided by R1, R2, which would make sense, right? It's the angle that you traverse between R1 and R2. So we just do some fun math to get that. Okay, so we can find delta theta easily, but we need z. Then everything will fall like dominoes. Okay, what do I mean by that? If we know z, well, first of all, if we know delta theta, we can compute a. If we know z, we can compute y of z and c of z and s of z, and then chi. And if we know chi and c of z and s of z, then we get f and g dot. And if we know the Lagrange coefficients, we can go all the way back up here and solve for V2. So everything hinges around this letter Z. So let's try to figure it out. There we go. All right, I'm on to my next page here. We will iterate to solve Z. So we will begin with an initial guess that Z is some small positive number. Then iterate. And this is where we're going to use that familiar kind of Newton's method, right? So we're going to say that Z, the next iteration is Z at the current iteration minus some function of Zi divided by the derivative of that function of Zi. So this basic method of iterating until conversion should look a little bit familiar. The functions are then going to be some fun combination of all of the other stuff that we've seen so far. And this is kind of the ugliest two equations that we're going to see today. And then we're actually done, basically. We can wrap up for the day. So f of Z, notice I'm starting all the way over here, which is not a good start. F of Z is y of Z over c of Z. And then all of this to the 3/2 power times s of Z plus a times the square root of y of Z minus the square root of mu times delta t. F prime of Z is y of Z over c of Z to the 3/2 in parentheses 1 over 2Z in parentheses c of Z minus 3/2 s of Z over c of Z close parentheses plus 3/4 s of Z squared divided by c of Z close parentheses plus a over 8 3 s of Z over c of Z square root y of Z plus a square root c of Z over y of Z close parentheses. There it is. Not pretty, but it is something that we can compute. So what this means is if we know Z, we can compute f of Z and f prime of Z. And once you've typed these up once, you'll never type them up again. And if we know f of Z and f prime of Z, we can iterate until we converge for Z. If we know Z and we have delta theta, we can compute A, we can compute Y, we can compute chi, we can compute S of Z, Z of Z, we can compute the Lagrange coefficients, and ultimately we can solve for V. So it all falls into place. And given that the solution is this ugly, I feel very bad for Lagrange and all the math that he would have had to go through to prove that this is the case. So our procedure, and after all this, it's still called Lambert's problem. Our procedure for solving Lambert's problem is, number one, using R1 and R2, find delta theta and A. Number two, assume that Z is some small positive value. And then iterate until convergence using the equations f of Z and f prime of Z. Number three, find y of Z and chi. Number 4, find only the necessary, we don't need all 4 of them, the necessary Lagrange coefficients F, G, and G dot. Okay, so we're going upstream. Finally, we can find V2, or I guess you could find V1 if you want to. And then finally, if desired, R2 and V2 can be used to find the true anomaly at the second time, E, A, omega, I, and omega. And that's it. So a little bit ugly. If I had all the time in the world, I would go back through and try to clean up this derivation, but I'm afraid that given our time constraints, I have to kind of throw this rather ugly looking abridged version at you. But ultimately, what I'm trying to get across is that someone else who lived hundreds of years ago, these people did this on parchment, by the way, with feather quills, and they figured this out. And certainly no calculators, right? That the procedure for solving Lambert's problem is something that you can code up. This is, by the way, one solution to Lambert's problem. There's other solutions, and finding ways of solving Lambert's problem faster and faster and faster is actually still something that people look into in terms of computer science. But this is a solution that you can code up. It's in the book if you took orbital mechanics at RPI. This is something that you would have at least would have spoken about in class, right? If you know R1 and R2, you can find delta theta, find A, find F and F prime, iterate until Z converges, find Y of Z, find chi, find Lagrange coefficients, find V2. Ultimately, we can solve the problem if you know R1, R2, and delta T, find V2. And also, going back even further, we can solve the problem if we have R1, R2, and R3, we can find any of the velocities. So those are 2 methods of initial orbit determination. Next class, we will go over the 3rd method, which is Gauss, and we'll at least talk about Gooding. We won't go into a ton of detail on it. And I hope that that only takes half the class, and we can spend the second half on something called matrix vector calculus, which is a lot of fun. And that is kind of the end of our introduction. And after that, we'll be on to estimation theory. So I'm going to stop the recording, but I'm going to stick around to answer any questions and, of course, talk about homework 1. So appreciate y'all sticking around and being patient with me through those derivations. And if there's nothing else, then class is dismissed.